Welcome, ladies and gentlemen. Let's begin our discussion today by considering the graph of f who's shown and answer certain qualities about it, like f of -3. Well, f of -3 is simply the y value, the function value returned at an x-coordinate -3. So get ready and be ready to share with the class when I call on you. So number 1, f of -3. Go ahead and tell the class when I call on you. Riley? 2. So f of -3 would be, well, that's the y value. The function right there is 2. Thank you, Riley. Raise your hand if you have the same. So we had 2 for the first one. Great. F prime of -3 is a distinctly different question. That's not asking the y coordinate of the function at x equals -3, but rather the value of the derivative f prime when x equals 3. And we know that f prime represents the slope of my original function anywhere along it. So go ahead and state the value of f prime of -3 when I call on you. Kobe?
0.
0. Raise your hand if you have the same as Kobe. 0. 0 is the slope of the tangent to the curve at x equals -3. The slope there is 0 because it's a part of a horizontal line segment there. Good. F prime of 4 then, right? F prime of 4 refers to the slope of the original function f when x equals 4. And what did you get for that? Right? What did you get for that? Anna?
5/2.
5/2. And we could get that because it was a line segment. We could count 1, 2, 3, 4, up 5 and over 1, 2, so 5 halves. Nice job. Raise your hand if you had 5 halves for number 3. 5 halves. Great work. What about f prime of 5? That is the value of the derivative when x equals 5. And I saw, Jake, what happened with that one?
Doesn't exist.
Yeah, it does not exist, right? And why doesn't the value of the derivative exist at x equals 5, right? What's going on there? Savannah?
It's a cusp.
Yeah, there's a corner, a kink, a cusp. Remember, a cusp is an abrupt change in direction on my original function. So because there's a left-hand slope value, 5 halves, that's not matching the right-hand slope value, right, 0, there's an abrupt change in the slope values, then this is not differentiable at x equals 5, so this does not exist. Right? This does not exist. Nice job. Thank you, Jake. Good work. All right, we can also consider the values of definite integrals graphically. We could interpret the definite integral from -5 to -1 of my function f, right, as summing up the area in between the function and the x-axis in between -5 and -1, such that area above counts as a positive contribution and area below counts as a negative contribution. So let's everybody go ahead and look at x equals -5, my lower limit. We'll scan the region from left to right as we move from the lower limit to the upper limit. -1 is here. And consider the area in between the function f in red and the x-axis using shapes that we know, and it looks like that's in here. So I'm getting 1, 2, 3, 4, 5, 6, 7.5 is what I was going for. I was going for 7.5. It looks like that's a little bit off, but I was going for 7.5. So raise your hand if you had 7.5. We all type that? Awesome. So we could write 7.5 about. And that would be square units, but we won't include the units right now. And then -2 to 3. -2 to 3, so that's a different problem. That's starting here and scanning to the upper limit of 3. And now area above counts as a positive contribution. Area below is going to count as a negative contribution. So it looks to me like this area below, right, is going to cancel out that positive contribution from the corresponding area above and leave me with a net value of that definite integral is -1, 2. Are you guys getting -2? So my final answer would be -2 for number 6. Raise your hand if you had that. Did anybody get -2? Good job, you guys. This canceled out the positive area, and then I left with that net result right there. Nice job. So I'm going to go ahead and box this because we want PDFable, of course. And number 7, the integral from 3 to 1, right? What's different about the limits on this one? What's different about the limits on this one? Paul?
You start at 3 and then go to 1, so that would go the other way.
Absolutely. So here, when we begin scanning from x equals 3 towards x equals 1, we're going from right to left, right? We're going from right to left, which is going to produce small incremental step delta x values that are now negative, right? That's opposite of our regular interpretation of scanning a region from left to right. So this negative, right, this area beneath the x-axis, which normally counts as a negative contribution, because we're scanning in the opposite direction, that is from right to left, it will now count as a positive contribution, that is the opposite. So we can handle that a couple different ways. One way would be to simply rewrite this and take the opposite of and switch the limits. The opposite of the definite integral from now 1 to 3 of f of t dt is equivalent to the original. And so now the opposite of the negative 4 units would be positive 4 units. In either case, we'll get the positive 4. So raise your hand if you already had positive 4. You have positive 4 for that? Good job, you guys. Way to go. What questions do you guys have on today's Bellwork? All right, then please listen carefully. Next time, as you know, we have our Unit 5 test. The concept and skill guide, right, has a lot of different bulleted points there, a lot of different concepts and skills that you'll be assessed on. So we're not going to collect this now because I want you to keep it and use it as a resource to review over the weekend. So once again, we're not going to collect this. You hang on to it, but we will be turning that in next time. So Unit 6 prerequisite and skill review, you have not gotten that yet. You're going to get that when you take the test, and you'll pick that up afterwards. So we're going to put those on hold right now. You're not going to turn anything in today. I want you to keep it and use it for resources. Hannah?
You said OTL number 1 is not due until the day after.
Correct. And then that's not due until the day after the test, right? OTL number 1, you still have to do it, but I want you not to focus on that, right, until after the test. I want you to focus on your review stuff, and that way it'll all even out by the time we get to Wednesday next week. Does that make sense? Great question. So we're not turning in OTL number 1 next time, right? We're not turning that in next time. We're not turning that in until day 2. Everybody good? All right, let's go. So the Fundamental Theorem of Calculus Part 1, right, enabled us to evaluate definite integrals exactly and algebraically without a calculator using an indefinite integral. That is, if f is an antiderivative of g, right? I'm sorry. If g is an antiderivative of f, rather, right? That's what that first part means. If an antiderivative of f is g, then we can evaluate the definite integral of f with respect to x on the interval a to b by doing what? Well, we'll find that antiderivative function, in this case g, and we'll evaluate it at my upper limit. We'll evaluate it at my lower limit, and we'll subtract the two. So if I can find an antiderivative function for my integrand function f, we'll call that antiderivative function g, evaluate it at my upper limit, evaluate it at my lower limit, and subtract the two, then that will yield the value, the exact value of my definite integral of f of x from a to b. That's the Fundamental Theorem of Calculus Part 1. Today, we're going to add the Fundamental Theorem of Calculus Part 2, and it's built on this notion of f being an area accumulator, right? If we have an area accumulator function where I scan a region from left to right, I can accumulate area as I move along it, and we're going to use that as a springboard for our discussion, okay? So today, we're going to generate the Fundamental Theorem of Calculus Part 2. The second content objective is to generate the calculus definition of natural logarithm. So I want you to think back to the pre-calculus definition of a natural logarithm. We said in pre-calculus, everybody find this on your sheet, right? So we found this. Is this not on your sheet? Okay. It's just further back. Okay, so you don't have to find it then. I just want you to look. So in pre-calculus, we said that ln of x is equal to y, right? ln of x is equal to y if and only if what was true? Well, think back to the invisible base, right, on that natural log function. What's the invisible base on that ln? Brandon?
E to the y
Yep.
equals x.
Absolutely. And so the natural log of x is equal to y if and only if e to the y equals x. That was our pre-calculus definition of natural logarithm, right? Well, today we're going to develop the calculus definition of natural logarithm. In order to do so, we need the Fundamental Theorem of Calculus Part 2. So by the end of today's class period, we'll have the calculus definition of a natural logarithm, and that's going to involve an integral expression, an area accumulating expression. So that's where we're headed for our second content objective. And we've got 3 different places to earn stamps. And so everybody, I want you to know there's 3 different places to earn stamps today. Ready? The first place is your FTC Part 2. That stamp, where did my black marker go? 6B. So that's our first place. 6B on the FTC Part 2 activity. 6B, everybody find it, and not the practice. right? It's not the one that says practice, it's the one that has the pictures of that square root function.
Fundamental Theorem of Calculus Part 2.
Yep. Fundamental Theorem of Calculus Part 2. Next, a new definition for natural logarithms, right? We're going to go ahead and earn stamps for that on number 5. So that's our calculus definition for natural logarithms. That's 6.2, right? 6.2 natural logarithms. Everybody find that? Circle number 5, that's our stamped eligible item on that one. And then the final place we can earn stamps is the practice, and that's last, okay? That's after we've come together and we've made sure that we got the Fundamental Theorem of Calculus Part 1. We've done some examples together. We made sure we got the new calculus definition for natural log. We've talked about that together. Then we'll turn you loose for a final time and we can earn stamps on number 4 and number 8 of the FTC Part 2 practice. And so everybody find that practice sheet. 2 stamps on there for a grand total of up to 4 stamps today. Okay, 1, 2, 3, 4 stamps possible to kick off our Unit 6. Questions about where you can earn stamps? Then what we're going to do is go ahead and jump into our FTC Part 2 with your cooperative learning groups. After everybody's gotten their stamp from 6B and 5 definition of natural logs, then we're going to come back together and we're going to have some whole class examples. Then you're going to break up one more time with your partner and practice on on the FTC practice Part 2. So everybody, I'm going to pause the recording and go ahead and scoot into your desk and get going. So in example 1 on our note sheet, we're asked to differentiate an integral, right? An integral defined expression. Well, what do we know about differentiation and integration? They're inverse processes, right? They undo one another. And so if we're going to find the derivative of an integral defined expression, it's going to give me simply that integrand function. If I found an antiderivative for cosine of t and evaluate my upper limit, evaluate my lower limit, once I differentiate those, I'm going to get right back to where I started, with the key difference that now I have an x in it. So this is as easy as rewriting, but now with my independent variable x substituted into my integrand function. It's that easy. In example 2, we're asked to differentiate an integral defined expression. Well, that derivative, that differentiation undoes the integration. If I were to go and find some antiderivative function for 1 over 1 plus t squared, and in this case we actually could, evaluate my upper limit, I get a function of x. Evaluate the lower limit, I get some constant. And then when I differentiate that antiderivative function with respect to x, I get exactly back where I started. I have my integrand function. With the key difference that now I would have my independent variable x in there. And so guess what? This is as easy as rewriting my integrand function, except everywhere I see a t, you're not going to put a t. What are you going to put? X. That easy. Annika.
I'm still a little confused why you switch from t to x.
That's a great question. So let's suppose, and we don't have to do this, right? Let's suppose we want to do this a long way. In fact, this one we can. We can do this a long way. Can we find an antiderivative function for my integrand function? Right? 1 over 1 plus t squared. What's the antiderivative, right? What's the antiderivative with respect to t of 1 over 1 plus t squared? Brandon?
Would that be the tangent?
Almost.
Tangent of?
It would be the
Tangent of?
inverse tangent, right? Inverse tangent. So inverse tangent. Good. Inverse tangent of t. Right? So we found an antiderivative function, but this was not an indefinite integral, but rather a definite integral. So what do we need to do? We need to evaluate that antiderivative function at my upper limit, at my lower limit, right? And then subtract them. So this original expression in the integral part, right, the red portion, is given by inverse tangent of what? X minus inverse tangent of 0, right? Now we differentiate it. We're really taking the derivative of this. Aren't we taking the derivative of this? Which means we're taking the derivative of this. To be equivalent to my original expression, the derivative with respect to x of the integral from 0 to x of that integrand function with respect to t. So what happens when I differentiate inverse tangent of x? What would I get? Oh, gosh, I know my rules, don't I? The derivative of inverse tangent is 1 over 1 plus input squared times the derivative of the input, and the derivative of the input x with respect to x is just 1. So I'm getting this minus, what's the derivative of The inverse tangent of 0, which is just 0. What's the derivative of a constant?
0.
0. My lower limit, if it's a constant, right, will always result in a constant when you evaluate my antiderivative function, which will always drop out when I differentiate it. So what do I get? Whether I did a long way or a short way, I still get the integrand function, but with the key difference that now I have x in it, my independent variable in it. Does that help? You can do it the long way, but sometimes we don't have, right? We don't have a antiderivative rule. Sometimes my integrand function is, we're unable to find a symbolic representation of the antiderivative, and so we would have to know how to apply the fundamental theorem of calculus part 2. Such is the case with the chain rule. In this case, I don't know what little f of t is, okay? I don't know what little f of t is. However, I do know that if I could find an antiderivative function, right? If I could find an antiderivative function for little f, I would call it big F. And I would evaluate it at my upper limit, and I would evaluate it at my lower limit. In this case, my upper limit is a composite function. It's not just x, what is it? Well, it's h of x. Right? Is it an h of x is my upper limit? What's my lower limit? Some constant a. So that would be a constant. Right? If I were to go and differentiate that to generate the derivative of g, call it g prime of x, I'd be differentiating big F of h of x. And I'd be differentiating f at a, some constant. Well, what's the derivative of a composition of functions? Right? What's the derivative of a composition of functions? Brandon?
The derivative of the function of the derivative of the big function
Yes.
of the little function
Yes.
times the derivative of the little function.
Absolutely. It's the chain rule. And so the derivative of this overall function, big F, evaluated at h of x, is going to be little f, evaluated at my upper limit h of x, times, you guessed it, the derivative of my inner function. What was my inner function? H of x, and so h prime of x. So the fundamental theorem of calculus part 2, that is where I have a composite function as a limit, not just plain Jane x, but some function of x itself, like x squared or 3 sine x, right, is going to be the integrand function evaluated at my upper limit, then times the derivative of my limit, right, times the derivative of that upper limit. So it's integrand function evaluated at my upper limit, and then times the derivative of my upper limit. Let's see what that looks like in practice. So let's go ahead and see what that looks like when applied to an upper limit that's not just plain Jane x. Here we go. If g is given by the integral defined expression from -2 of sine of x of 3 minus m squared with respect to m, can we find g prime of x? That is the derivative of that integral defined expression? Yes, most certainly we can. It's simply going to be my integrand function evaluated at my upper limit, then times the derivative of my upper limit. What would that look like? Well, I'll simply rewrite my integrand function, right? Except everywhere I see an m, I'm not going to put it. Everywhere I see an m, I'm not going to put an m. What am I going to put?
X.
Sine of x. I'm going to put sine of x, my upper limit. And then, because it wasn't just x, I'm going to multiply by the derivative of my upper limit. What's the derivative of my upper limit? Cosine of x. That's it. So I get quantity 3 minus sine of x squared, all times cosine of x.
You would just leave it like that.
I can just leave it like that, right? I can just leave it like that for right now. If we had to simplify, we could simplify, but I want to see exactly where this is coming from. Try another one. The derivative with respect to x of the integral from 1 to x squared of cosine of t dt. Right? Go ahead and see if you can, with your group, puzzle out what this would be. So try this one with your group and see if you can figure out what the derivative of that integral expression would be, and be ready to share. MBD. All right, so what do you guys think this is, right? What do you guys think this is? Kobe?
Cosine of x squared times 2x.
Cosine of x, my integrand, I'm sorry, cosine of t evaluated my upper limit is cosine of x squared times the derivative of that upper limit, 2x. Absolutely right, Kobe, thank you. Who had 2x times cosine of x squared, or cosine of x squared times 2x? Both are correct. Way to go, you guys, that's it. So we can now find the derivative of an integral defined expression, whether my limits, right, whether my limits are variable terms, right, or just x, or a composite function. So then, what happens if we had, right, the integral from x to 5 of 3t sine t with respect to t, right? What's different about this function? What's different about this one? A couple things, right? A couple things are different about this. What's one thing that's different? What's different about the limits here? Sophia?
X is the lower limit.
Yeah, x is the lower limit, right? In my fundamental theorem of calculus here, we've had my variable be the upper limit always. So can we handle that? Well, certainly. Can we rewrite our original y by applying our properties of definite integrals, which allows us to flip the limit so long as we include what? The negative sign. So this is the same as the opposite of the definite integral from 5 to x of 3t sine t with respect to t. The other thing is that we don't have, right, symbolically, we can't find an antiderivative function for this 3t sine of t. We don't have an antiderivative rule, right, to undo this product yet. And so at this stage in our lives, we're unable to find an antiderivative. Does that matter if we're trying to find the derivative of this? No, it doesn't matter. It's simply going to be the integrand function evaluated at my upper limit, right, and then times the derivative of my upper limit. Because my lower limit is a constant, if I could find an antiderivative function and evaluate it, then that big F of B, I'm sorry, that big F of A is just going to be some constant, all right? And when we differentiate, we'll get 0. So this is simply going to be so dy dx, the derivative of that, is simply going to be negative, and then it'll be 3x sine of x. That is the integrand function evaluated at my independent variable. That's it. We didn't have to find an antiderivative in order to apply the fundamental theorem of calculus part 2 because it says explicitly the derivative of an antiderivative is the original. Oh, I love it. Uh-oh. Just when things were going okay, right? We can handle a constant now on top and a variable on bottom. We've even handled chain rule. Now what happened? There's no constant, right? There's no constant. That's okay. Instead of having the derivative of my lower limit drop out, right? I'll just have my derivative of the lower limit now be a function of x. And so it's just that I'll have x's in both of these expressions and the subtraction in between. And so even if I can't find an antiderivative function for this symbolically, I know that if I were to find an antiderivative function and then differentiate it to get dy dx, right? It would get me right back to this original integrand function with the key difference that it would be evaluated at my upper limit, right? So now I have an x squared there times the derivative of the upper limit, a 2x, and then minus, and I have that integrand function evaluated at my lower limit, and then times the derivative of that lower limit. What? Well, let's see what that looks like. dy dx would be given by integrand function evaluated at my upper limit times the derivative of my upper limit minus integrand function evaluated at my lower limit times the derivative of my lower limit. What's that? 2. And so while that doesn't look very pretty, we could do a rewrite. And that still doesn't look very pretty, but it's better than the one above. That is the trickiest thing you'll see, right? And I've seen a multiple choice question that looks like that. That was really one that separated, right? That separated students. They put it there. But again, it's just fundamental theorem of calculus, right? Part one combined with differentiating integral expression. Part two, you don't get my answers. Does everybody see where the subtraction comes from? Right? The subtraction comes from upper limit minus lower limit, and the derivative, taking the derivative with the chain rule. Awesome. Okay. So we're a little bit crunched for time because of our 2-hour early release. In fact, our class period ends at 10:30, and so that's just in about another 9 minutes. And so, in terms of using our time best, so I think using our time best is to stay right where you are in your groups, and then work on your natural log one together, right? Working towards your 5 stem. When you get that 5 stem, right, then you'll be able to do the practice. So the best thing I think for us to do is to stay right where you are in your groups, and continue on your natural log so you can generate the definition of the natural log function in terms of calculus and integral expression. And now we can do that because we have the fundamental theorem of calculus part 2. So let's go ahead and close out today while you're working in your groups on 6-2, okay?
Good job.